All right. So last week, Friday, we left off talking about confidence intervals for means. So what we discussed was kind of the build-up when they tried to do confidence intervals for means. What were some issues that they ran into? So the first issue was we don't know the population standard deviation, which is required to calculate the standard deviation for our sampling distribution. So they decided, well, let's make that fix by just using the sample standard deviation. So we will have collected a sample, calculated sample mean, so let's use sample standard deviation. But then even then, they realized that when they used that formula to create their confidence intervals, they were making way more mistakes than they should have been making based on what they were looking at. So we had a guy figure out the correction, and it was instead of using a normal distribution, so instead of using normal distributions like we did for proportions, he noticed that when we use sample standard deviations, so when we use the standard deviation from just our sample alone, we actually created a different type of distribution. So it was one that was still symmetric, it was still bell-shaped, but it had more area in the tails, less area in the medial or the middle. Okay? And so what happened was we created a new distribution called the t-distribution, and that t-distribution was actually a family of distributions based on the sample size that you collected. So each sample size corresponds to a different t-distribution, has a different spread, different t-values, and so on. So once we traded out z for t, that tended to fix just about everything they needed it to be to fix. So what we're going to discuss today is how to actually go about calculating and interpreting the confidence intervals for means. So in order to create a confidence interval for means, you have to have three conditions that are met. So before we even start working with the confidence intervals and the t-stars and things like that, we have to make sure our conditions for inference are met. So the random condition is just like it always has been. The sample we collect must be random, so we must have collected an SRS. Okay? What else do you think we're going to need to check? 10%. Just like we did earlier, we have a 10% condition. The sample that we collect must be less than 10% of the entire population in question. Okay? And then the next one is one we call the normal condition or the nearly normal condition. And this is pretty much the exact same condition as what we had for the large enough condition back in sampling distributions. And that is that our sample size has to be larger than, or at least 30, or we need to have a normal distribution to begin with. So when you check that third condition, there's two different criteria to account for. If they tell you that the original distribution is normal or approximately normal, then you don't have to worry about sample size. You can use any sample size and you're going to be okay. But if they don't tell you anything about the population distribution, or they tell you that it's skewed, and you don't have a sample of at least 30, then you would not want to proceed creating the confidence interval with these methods. Okay? So you do not want to use these t-procedures if your sample size is less than 30 and your graph shows strong skewness or outliers. Okay? So one of the things that you're going to be doing now or this time, and we're going to have an example of it today, is there might be times when they actually give you the distribution. Here is the sample. And they want you to verify the conditions, or they want you to create the interval. So you would have to check this last condition. If your sample is less than 30, you're going to actually have to create a graph to show whether the distribution is normal or not. Okay, and we're going to talk about how to do that when we get to the example there. So we okay with that?
The last one talked about this, like, it was okay if like the number was close to 30, like 28 or something like that. Or...
It was only okay if the distribution was not strongly skewed.
So if it's lower than 30, it's stronger.
Yeah, in this case, we just want to stick to the, if it's less than 30 with any type of skew or any type of outliers, because this will be greatly affected with these intervals and things like that. So if you're less than 30 and you're not normal, don't do anything with it, okay? All right, so those are our conditions. So once we get through our conditions, the last thing we need to make sure we understand or figure out is what the actual formula for our confidence interval looks like. So, for sampling distributions, so back in chapter 7 when we did sampling distributions for means, the standard deviation was calculated by taking the population standard deviation divided by the square root of n. But as we discussed last Friday, since we're trying to create a confidence interval, that means it's implied we don't know our population values. We don't know our population mean or population standard deviation. So instead, we're going to calculate what we call standard error for x bar. So notice the change in notation to SE for standard error. So with standard error, we use the sample standard deviation divided by the square root of the sample size. So not much change. It's just instead of a population standard deviation being known, we use our sample standard deviation to calculate the standard error. Okay. So, once we know the formula for standard error, the formula for the interval becomes pretty straightforward, just like with proportions. The center of our interval will be the sample mean. So whatever mean we calculated from our sample becomes the middle. And then we take plus or minus our t star, and that t star is based on the degrees of freedom, which is calculated using the sample size. And then we multiply by standard error. So the sample standard deviation divided by square root of n.
Wait, so with the T star DF,
Mhm.
you do where the
So this is just this notation, the t star
yeah.
is just that's like z star, but then the degrees of freedom down here just is a reminder that you have to know the degrees of freedom, which would be n minus 1.
So that doesn't, in the equation, you don't do anything with it, right?
Not in the equation itself, no.
Okay.
In the degrees of freedom only tell you how to look up t star. Okay, so yeah, it's not going to be part of the actual calculation. It's just there so you know which t distribution you're using.
So it's just T star times SE.
Okay. So let's put it into practice. So in the example here, environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides, which they call NOx. So researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675, and the standard deviation was 0.3332. So it says construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. Okay? So they tell us what they're measuring. They tell us that the sample size was 40. We have the mean and the standard deviation from the sample. So they give us all that information here. So if we want to construct and interpret the 95% confidence interval, what's the first thing we would need to do? Check the conditions. Okay? So the first thing we're going to do is check our conditions. So, first condition was random. Do we know for certain that this was a random sample? Yeah, because it says random sample. So it says they took a random sample. 10%. So our sample size was 40. Would that be less than 10% of all light-duty engines of the same type? Yes. So we should be good there. And then for the nearly normal condition, 40 is greater than 30. So in this case, they don't actually mention anything about the distribution, right? So they don't say it's approximately normal to begin with, but since we have a sample size larger than 30, we're okay to proceed. So when you write these out again, remember, you need to make sure you mention each one and how you know it's met. So the random condition, we see the actual phrase, random sample. With the 10%, 40 should be less than 10% of all light-duty engines. And for the normal condition, n equals 40, which is more than 30. Okay? So on a quiz or test or in your homework, you would need to have all of these things listed out. Okay there? Okay? So once we have our conditions checked, our next step is to calculate our three values. Well, we already have the mean, so we already have x bar that was given to us here. We need to calculate t star, so that's a value we definitely need yet. And we would need to calculate standard error. Okay, so we have standard deviation from our sample, but we need the standard error in order to plug into our formula. So go ahead and calculate t star for this scenario. So either using the table or using your calculator. Get your t star value for this particular scenario.
It's 40.
Oh, okay.
How do you do it? It's way easy.
It's 2.042.
Yeah, I know. Guess what? I already wrote that.
Then why ask?
All right. So what do you get for t star? 2.023. Did I get 2.023?
No.
Okay. So, depending on which method you used, we would have different results, right? Because when you look at the table, 39 degrees of freedom doesn't exist, right? And even though 39 is almost 40, we don't have a sample size large enough for 40 degrees of freedom, so we have to use the value smaller, okay? So if you used your calculator, you get to 2.023 because you can use exactly 39 degrees of freedom. If you use the table, you get 2.042. So does 2.042 match up with what you got? Okay, so if you didn't use the calculator, that's what you get. Now, as far as like homework, quiz, and test go, on like a quiz or a test, I'll have both ways worked out. So whichever way you choose, I'll have it worked out that way as well. So that way you're not getting any mistakes or anything off based on that alone. Okay? But remember, when you report your T star, make sure you also denote how many degrees of freedom you use. So since you use the table, you can only have 30 degrees of freedom in your calculation. If you use your calculator, you have 39. So make sure you label your T star correctly. Everyone okay with that? What are you putting in for your area? Okay. So for 95%, the 95 would be the middle, right, plus the tail. So if you don't want it, table should be always an option. All right, so once we have that information, the rest just becomes plugging in and reducing down. So depending on which method you use, table or calculator, there are two different calculations, okay? So x bar, that's the value that came directly from the problem. So they told us the sample mean was 1.2675, so we plug that in. If we use the table, we got a T star value of 2.042, and then for standard error, they told us the standard deviation was 0.3332 divided by our sample size, so divided by that square root of 40. So then when you plug this into your calculator, again, the easiest way to do this, so that you do it in order of your interval, is take the 1.2675 minus the product of t star and standard error, and then do 1.2675 plus that product. So just plug it straight in your calculator and get the two
Is there a way
values.
to like do it in your calculator like it was the last one?
Yes, and we'll talk about that tomorrow probably. We're going to do the formula today, we'll talk calculator tomorrow. Okay?
I don't like that.
I think it's on two of them.
So, here would be your interval if you were using the table with your t star. If you use the calculator where you can be more accurate with t star, you do the same process. The 1.2675, t star would have been 2.023 times standard error, and then again you do a minus to get the lower bound, plus to get the upper bound. So you would get the interval 1.1609 to 1.3741. So everyone okay with that? So as far as the process goes, once you check your conditions, your next step is to calculate the three pieces. So the mean should be given to you. T star you get from your table or calculator. Standard error is just plugging into the formula. And then it's just a matter of plugging it in, getting your values. Okay? Now, if I wanted to interpret this interval, so if I was going to interpret my confidence interval, what would I need to say? Pretty much. We can use the same statement we had before. So we are 95% confident that the interval from whichever two you get, right? So 1.16 to 1.37 captures what? The true mean amount of NOx emitted by light-duty engines of this type. So remember, when you get to that context part of the interpretation, make sure you go back to the question. It tells you exactly what you're trying to measure. So you're looking for the true mean amount of NOx emitted. Okay? So if you like that blanket statement from the previous section, you can still use that for means like you would for proportions. It's just a different wording as far as context. Okay? So, the way I worded this, I did it a little bit differently. I didn't use that general blanket statement. So I said we're 95% confident that the true mean level of nitrogen or NOx emitted by this type of engine is between 1.1609 and 1.3741 grams per mile. Okay? So one of the things you want to make sure you do when you're doing this interpretation portion, so whether you use the blanket statement or whether you rearrange it a little bit like I did here, you need to make sure you put units with your answer now. So with proportions, we didn't have to worry about that because proportions came out as percentages. So there were no units to work with. With these, we do have units of measure, which means we have to include those in our interpretation of the interval. So make sure, regardless of where you put the interval in, you have units of measure that go along with it. Okay with that? Okay. Any questions on the process? All right. So let's do another type. So another example, creating a confidence interval. Now this one's a little bit different. In the last example, they gave us our summary statistics. So they told us the sample mean, they told us the sample standard deviation. They just had us use that to calculate the correct interval. This time, we're working with something a little bit different. This time they actually give us the data. So here they're actually giving us the measurements. We have to come up with everything we're going to need then for our interval. So, the example, a manufacturer of high-resolution video terminals must control the tension on the mesh of the fine wires that lies behind the surface of the viewing screen. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent into the production process. So here are the tension readings from a random sample of 20 screens from a single day's production. So they just have random samples or random tension readings from 20 randomly selected screens from that single day's production. Okay? So they want us to use those pieces to construct and interpret a 90% confidence interval for the mean tension of all the screens produced on this day. Okay? So we want to construct the interval for the true mean tension of all screens produced on the day. So, if this is what we're going to be working with, the first thing we need to do is check your conditions. Okay? So before you start, because when you do these types of problems, remember, if you run across those conditions and something's not met, you don't do any of the actual work. The T procedures won't work in those particular situations. So, as far as the random condition is concerned, it said a random sample of 20 screens, so we're good there. The 10%, 20 screens should be less than 10% of all screens produced that day. Now, the normal condition. We have a sample that's less than 20 or less than 30, and in the problem, did it specifically say anything about an approximate normal distribution? No. So here's what's going to have to happen. Since our sample's less than 20 and they haven't told us what the distribution looks like, we need to figure out what the distribution looks like. Because they gave us the data. So we can check the normality of the data that we have. Okay? So to do that, in your calculators, you're going to put these values in to your list. So you're going to go to Stat and Edit, which you need to do anyway because you have to calculate mean and standard deviation. So take a couple minutes here, get into your lists, put these 20 values into list 1. And as you do it, make sure you're very careful that you don't make any mistakes. Because even the littlest mistake in the entry here will create large differences later on. So take your time and enter these correctly. It doesn't matter what order you go in. So you could do up, down, up, down, up, down, all the way down, or just all the way across, all the way across. Doesn't matter. Because they're all going to go into list 1. So it's all part of the same list. Yep. Yeah. Yeah. So all these values should be going into list 1 for your screen.
Yeah, I bet you might Not bad. Feels bad.
Get done early, wouldn't hurt just to run back through real quick, make sure you didn't make any typing errors.
How do I clear my old one? I thought I would
each individual spot. No. So then, so once you get to like 21, then just keep deleting until they're all gone. Otherwise, if you do it before you start entering your own list, you can just highlight it to go up to list 1 and hit clear.
I should know.
Yeah. All right, so how are we looking? All right, so once you have in your list, what we're going to do is we're going to check this normality, which means we need to check a graphical display of some kind. Okay? Now, as far as checking for normality, the easiest one, in my opinion, is what's called the normal probability plot. It's one that we talked about last semester. Okay? So, to kind of refresh your memories on how to create a normal probability plot, once you have your data entered into your list, you're going to go to your stat plot, so second y equals. You're going to choose plot 1, and make sure to turn it on. So make sure on is actually highlighted, so hit the enter button on on. What's that? You might. Yeah, if you have other ones on, you might need to turn them off just so they're not trying to do multiple exits. Okay? So then the next thing is you have to choose the type of graph you want. The normal probability plot is the, anybody remember?
Last option.
The last option. So the normal probability was the last option. So scroll right all the way until the end. Looks like it's going to create like a scatter plot. And so when you select that option, it should ask what list you want to use. So you're going to make sure it says list 1 or whatever list you entered your values into. And then how do we get the correct window? Zoom 9. So then once you have everything selected correctly, go zoom 9.
Extra line there.
No.
So this is what I got. This looks like a plot. I don't want it. I don't want it. Let me see. Oh, that's so wrong. They're lying to my face.
Oh, you guys are wrong. I really like this. The last one.
You're lying to
All right, so when we check, you guys should get something that looks somewhat like this, right?
What is that? I don't think this is right.
They're kidding.
Everyone get something like that?
I don't think that's
You're wrong, Reba.
All right. So if you didn't get this, once we're done with the stuff, we'll go back through this individually and get you figured out, so why they were messed up or whatever. But this is what we should be looking at. Now, what we're looking at on the normal probability plot is basically for a linear pattern. Okay, so we just want to make sure that it's linear. And when we do that, again, remember, we don't care about little waves throughout. We're looking at overall, does it appear to be fairly linear in nature? Okay, so you're looking to make sure that there aren't any huge curves over the entire span of the data. So does it appear that we're fairly linear? Yeah. So the normal probability plot is fairly linear, which means our sample data is fairly normal. Okay? So even though we have a sample size less than 30, we have a fairly normal distribution to work with, so we're okay to proceed. So one of the things you guys have to do on a problem like this, if they give you the data, is you have to check that normality. If your sample isn't at least 30, you have to show your normal probability plot. So just give me a sketch of what it looked like. If they don't give you the numbers, so if we don't have the data and they don't say anything about normality and their sample size is less than 30, then you'd have to stop. You'd have to say, we don't have any way to verify the normal condition, we can't proceed. Okay? So on one like this, where they give you the data, you have to check. If they don't give you the data, there's nothing you can check. Okay? All right, so conditions were met. Now we need to calculate T star, X bar, and SX. So T star, you can use your table or your inverse T. X bar and SX, how are you going to calculate those the easiest?
Calculator, 1 bar.
The 1 bar stats. So go to stat, over to calculate, choose 1 bar stats.
There have been no conditions in there.
Because random sample, 20 is less than 10%,
Oh, you just did that.
and then we just did normality. Yeah.
So what was the graph in part 4?
That's to check the normal. Because our sample size is less than 30, and if we're not at least 30, then we have to know what type of distribution we're looking at. So if it's normally distributed, then we're good to go. If it's not normally distributed, then we're not good.
How did this show us that's normally distributed?
Because the normal probability plot is linear. So you're just looking to make sure that that normal probability plot is not
Way outside. So this isn't considered way outside?
No, because it's falling in line with everything else. Yeah, it's just falling in line. All right, so when you calculate X bar, should come out to be 306.32. SX should come out to be 36.21. And then for T star, we use 19 degrees of freedom, which, whether you use your calculator or your table, should come out to be the same, which would be 1.729. So once you have all 3 pieces of information, you go ahead and plug those pieces into your confidence interval formula. So you plug in 306.32 for X bar, 1.729 for T star, SX 36.21 over the square root of the sample size 20. And then so from there, you would actually do your minus and plus, get your 2 values for your interval, and you end up with the interval from 292.32 to 320.32. Okay? So once you have all the pieces you need, it's just plug and chug. Okay? Now, once we get the interval, 292.32, 320.32, when we want to interpret, we would say what?
90% confident that the interval between blah blah.
Okay, so we're 90% confident that the interval from 292.32 to 320.32 what? What are my units? Millivolts. So the interval from 292.32 to 320.32 millivolts should capture the true mean tension of all the screens that day. Okay? So, another way of interpreting that, we're 90% confident that the true mean tension in the batch of video terminals produced that day is between 92.32 and 320.32 millivolts. Okay? So don't forget units with your interval now, since we're talking means, and then don't forget the context, the true, mean, whatever from the problem. Okay? Okay with that? All right. So for tomorrow, I want you to try out the following problems here.